Hello everyone. In this video lecture, let us discuss about the topic of mathematical modeling of mechanical systems under the unit 1 of control systems. Objective. The main objective of this video lecture is to introduce the components of mechanical systems and the representation of the mechanical systems. Introduction. A physical system is a collection of objects connected together to serve an objective. Example, electronic amplifier, communication satellite. For analysis and synthesis purpose, a system has to be represented with its full properties, but not possible practically. So, idealizing assumptions always made on physical system. An idealized system is called physical model. So a communication satellite can be modeled as a point, a rigid body or a flexible body depending upon the study to be carried out. So accurate model cannot be obtained by removing the idealizing assumptions, can change physical model to mathematical model. Mathematical representation of physical model by using appropriate physical law. These models are the foundation to analyze and design of control system problems. Analysis of control system means finding the output when input and mathematical model are known. So design of control system means finding the mathematical model for the known input and output. So no mathematical model of the physical system is extract. The transfer function. The transfer function is a system is defined as a ratio of Laplace transform of output to Laplace transform of input with the zero initial conditions. So here the system is a time domain representation of this system. So where R of t is the input signal and C of t is the output signal of the system. So this is a Laplace transform representation of the same system. So instead of here R of t, the Laplace transform is R of s. Here C of t, that is C of s. So for Laplace transform of x of t is nothing but x of capital X of s. Similarly, for differentiation of the x of t, for this one is s into x of s, and then double differentiation, that is d square x of t by dt square. For the Laplace transform for this one is s square into x of s. Next, mechanical system. There are two types of mechanical systems. One is a mechanical translation system and another one is a mechanical rotational system. So what is a mechanical translation system means? The motion takes place along a straight line. So this is a mechanical translation system. Whereas in the rotational system, the motion takes place about a fixed axis rotation. So the equations of the motion for mechanical systems can be formulated by using Newton's second law of motion. So next, what are all the elements are presented in the mechanical translation system as well as rotational system. So both the system having three elements. One is a mass, another one is a dashpot or damper, and then spring. So first, what is a mass? Mass is a property of a body which stores kinetic energy. If a force is applied on a body having a mass m, then it is opposed by an opposing forces due to mass. So this opposing force is proportional to acceleration of the body A. So the assuming elasticity and frictional are negligible here. So that for Fm is directly proportional to A, so that the proportionality constant here is m. So m into A. So A is the acceleration. So whereas m is the mass and then Fm is the opposing force due to mass. So in terms of acceleration, in terms of displacement is nothing but d square x by dt square. So that the equation becomes F is equal to Fm, which is equal to m into d square x of t by dt square. So whenever mass is presented in a mechanical translation system, you can write like this for the equation, that is mathematical equation. And then similarly, next one is the moment of inertia. This is for the one of the element for mechanical rotation system. So here the instead of here, this is a force is applied. Instead of force, here the torque is applied to this moment of inertia. If the torque is applied on a body having the moment of inertia J, then it is opposed by an opposing torque due to the moment of inertia. So this moment of inertia stores kinetic energy also. So the opposing torque is directly proportional to angular acceleration of the body. So assuming the elasticity and the friction are negligible in this case. So where T is the torque, applied torque, and Tj is the opposing torque due to moment of inertia, and then J is there is a moment of inertia where alpha is nothing but angular acceleration and theta is angular displacement. Next, the second element for mechanical systems. So whether for the dashpot, for both rotational as well as translation system, the dashpot is presented. So here this represents by B. So one end is fixed, another one is free. So what is a dashpot means? So if a force applied on a dashpot B, then it is opposed by an opposing force due to friction of the dashpot or damper. So here the Fb is nothing but velocity of the body. Fb is not Fb is directly proportional to velocity, where proportionality constant is nothing but b here. So Fb is equal to b into v. So v is the velocity of the body. So in terms of velocity, you can write displacement. So b equal into dx by dt. So whenever the dashpot is presented in a mechanical translation system, you can write like this. So F is equal to b into dx of t by dt. Okay. So similarly for rotational system, instead of force is applied, here the torque is also applied here. So if the torque is applied on a dashpot B, then it is opposed by a torque due to rotational friction of the dashpot. Where here the TB is the opposing, that is opposing torque is directly proportional to angular velocity. So here also same, that is a proportionality constant is also b. So b into omega. Omega is nothing but angular velocity. Here in terms of angular velocity, in terms of displacement means d theta by dt. That is here the displacement is in terms of angular displacement. So the dashpot is presented in a rotational system. You can write like this. Next one is the last element. There is a spring. The spring is also one of the element which stores potential energy. If a force is applied on the spring, then it is opposed by an opposing force due to elasticity of the spring. The opposing force is directly proportional to the displacement x. So where k is the proportionality constant and Fk is the opposing forces. So next one is this is a whenever that is a torsional spring. that is presented in rotational system. So here the torsional mechanic, there is a translation mechanical system. The spring stress potential elements similarly in the rotational mechanical system. The torsional spring is stored potential energy. Here the opposing torque is directly proportional to theta. That means angular displacement. So the Tk is equal to k into theta, where k is the proportionality constant. So whenever the rotational system, the spring is presented, you can write like this, k into theta. Next one is the rules you have to follow for the whenever the writing the mechanical translation system or mechanical rotational system. First, identify the input variables and output variables. So next, all masses, that means or otherwise moment of inertia, will move independently and hence gives displacement to each mass. The ends are springs and dash parts will always moving with the displacement of the masses in which they are connected. The other ends of the spring and the dash part are dampers. If they are not connected to any fixed frame, then these free ends will move with different displacements. If they are connected to any reference spring, then the displacement is zero. At each variable point represents the various forces acting and equate the algebraic sum of all the forces to zero. Note, whenever the spring and damper elements are connected in series, assume zero mass in between them and give the displacement to that mass. Next one is the steps to find the transfer function of the mechanical system. So first, obtain the differential equation of the system at node. So node means meeting point of the elements. Generally, mass in mechanical translation system and moment of inertia for the mechanical rotational system. Assume displacement variables at masses, that means nodes. Draw free body diagram of the system. The free body diagram is drawing mass alone and marking forces acting on that mass. For each free body diagram, find the differential equation by equating the sum of applied forces equal to sum of opposing forces. So next, take the Laplace transform of differential equation, rearrange and find the ratio of output to input. Next, some of the examples for mechanical rotational system modeling. So in this problem, here the two masses are presented here. So one is mass M1 and mass M2. Here the mass M1 is connected with K1, B and K2. That means spring, dashpot and another spring. So the K1 is another end is connected with there is a fixed end. So but K2 is connected to the another mass, so that having some other displacement for that mass, so that will be Y2 here. So you can, what is the aim of this problem is you have to find out the Laplace, that is a transfer function. So transfer function is nothing but, already. So transfer function is nothing but the Laplace transform of the output to input is nothing but the transfer function. So here what are the first, you can identify the input and output variables. What is the input variables here? So f of t is the input, output is y2 of t. So you take the Laplace transform for this and find out that one. So find the our aim is find the transfer function for this one, so that y2 of s by f of s you can find out this. So next, you can draw the free body diagram for M1. So this is the free body diagram for M1. So what is the applied force? F of t is the applied force. Fm1, F Fk1, Fk2, Fb. So these are all the opposing forces for M1. Next, you can apply the Newton's second law of this M1. So write the equation. You know this Newton's second law. Algebraic sum of the opposing force is equal to algebraic sum of applied force. So now these are all the opposing forces and applied force is F of t. So that Fm1 plus Fk1 plus Fk2 plus Fb is equal to F of t. So you know already how the mass is presented. You can write the equation. So m1 into d square y1 of t by dt square plus k1 into y1 of t plus k2 into y1 minus y2, because you can consider this mass m1. So the initial displacement is y1 and final displacement is y2. So that y1 minus y2 plus b into dy1 of t by dt, which is equal to f of t, because the another end of b is connected in a fixed point. Okay, so this is, name it as this is the equation number 1. So taking the Laplace transform of equation 1 with 0 initial conditions, so we can obtain this m1 s square into y1 of s plus bs into y1 of s plus k1 y1 of s plus k2 into y1 of s minus y2 of s is equal to f of s. So rearranging and take the common factor from this these terms in y1 of s outside. So m1 into s square plus bs plus k1 plus k2 into y1 of s minus y2 of s into k2 of s is equal to f of s. You can name it as this is the equation number 2 or otherwise 1.2. Next, you can write the equation for the mass m2. So for a free body diagram, this one is a free body diagram for m2. So because the m2 is connected with k2. So here not applied for applied forces, only for opposing forces. So that Fm2 and Fm1. Fk2, not Fm2 and Fk2. Okay, so that in this you can write the equation. You can apply the Newton's second law. So Fm2 plus Fk2 is equal to 0. So now write this equation into a element. So that change into element. So because Fm2 is a mass, so m2 into d square y2. So this displacement is y2. So that y2 by dt square plus k2 into, you can consider this point. So that y2 minus y1 is equal to 0, because applied force is not presented here. So that this will be 0. So you name it as the equation number 1.3. Taking the Laplace transform of this equation 1.3 with 0 initial conditions. So that m2 s square into y2 of s plus k2 into y2 of s minus y1 of s equal to 0. You take it y2 of s for these two terms. So y2 of s take it outside. So that m2 s square plus k2 minus y1 of s into k2 equal to 0. So finding this equation y1 of s from that equation. So that m2 s square plus k2 divided by k2 into y2 of s is nothing but y1 of s. Substitute this y1 of s in this equation 1.2 and rearrange. You can obtain the transfer function of the given system, mathematical, that is a mechanical translation system. So y2 of s by f of s is equal to k2 by m1 s square plus bs plus k1 plus k2 into m2 s square plus k2 minus k1 square. So this is the final transfer function for the given mechanical translation system. Next we'll move on to the second problem. This problem is the modeling of mechanical rotational system example. So in this system, here J1 and J2s are presented here. So in between J1 and J2, we can connect K also. So and then dashpot is also presented in the J2. So another end of the J2, B is fixed end. Okay. So here the torsional, that is torque, is applied only for J1 here. Okay. So having two in moment of inertia means having two different angular displacement will be presented. You name it as a theta, means here you assumed this as a theta 1. So now you can draw the free body diagram. So what is the applied torque here? So here the applied torque is T, and the J1 is a moment of inertia for this one, J1, and then here the opposing forces is TJ1 and TK, the spring having the opposing force, so TK, and angular displacement here is theta 1. You can assume the angular displacement here is theta 1. So now by Newton's second law, we can algebraic sum of all the opposing forces equal to algebraic sum of all the opposing torque. Not a force or torque, because this is a rotation system. So that Tj1 plus Tk is equal to T. This is the Newton's second law of this mechanical rotation system. So corresponding equation is J1, because Tj1 is the moment of inertia J1. So J1 into d square theta 1 by dt square, because this displacement is theta 1, plus K into in between this the J1 and J2s are presented in K, so that having two displacement will acting this spring, so that K into theta 1 minus theta, because you consider J1 means theta 1 minus theta. Suppose you consider J2 means theta minus theta 1. Okay, is equal to T. You name it as the equation number 2.1. So next, taking the Laplace transform for this equation, and Laplace transform for this equation, you can write this J1 S square theta 1 of S plus K into theta 1 of S minus K into theta of S is equal to T of S, and then you take theta 1 of S common for these two elements. So J1 S square plus K into theta 1 of S minus K into theta of S equal to T of S. This is you name it as the equation number 2.2. Next, writing the another equation, that is considering J2, that is moment of inertia J2. So you can draw the free body diagram first. So for J2, only this only presented, but torque, opposing torque is Tj2, and also spring is presented along with this, so Tk. So and then theta. Okay, so now again opposing force is equal to applied force. Here the applied opposing torque is equal to opposing torque. So here the applied torque is not here, so that 0. So opposing torque is Tj2 plus Tk plus Tb. Okay. So because Tb is connected with J2. J2 is K and B also connected with this. So that these three elements having the opposing force, so that you can add these three opposing force equal to 0. So write it in the equation form, J2 theta d square theta by dt square, because theta is nothing but displacement for angular displacement for J2, plus b into d theta by dt plus k into theta minus theta 1 is equal to 0. So this is as a equation number 2.3. Next, take the Laplace transform with 0 initial conditions for this equation 2.3, and we can write this j2 s square theta of s plus bs into theta of s plus k into theta of s minus k into theta 1 of s is equal to 0. So you can rearrange and find this theta 1 of s is equal to j2 s square plus bs plus k divided by k into theta of s. This is as I name it as equation number 2.4. Substitute this 2.4 in 2.2 equations and rearranging, we get the final transfer function theta of s by t of s. So that is equal to k by j1 s square plus k, j2 s square plus bs plus k minus k square. So this is our final transfer function for the given mechanical rotational system for this problem. These are the references I referred for preparing this video lecture. Thank you for watching this video.